times e to the negative t times r over c. Means write this like this. Negative t times r over L. I think I wrote C. You get the idea. It was supposed to be an L. So, once again, e to the negative, and so if t is 0 at the beginning, at time 0, this is 0, so e to the 0, anything to the 0 is 1. So, at time 0, the voltage across the inductor equals the full voltage. Basically, when there has been no magnetic field developed at all, and you apply a voltage, it's going to completely counteract that voltage because the magnetic field corresponds to a current of 0. And then, at infinity, e to the negative infinity ends up being 0, so VL equals 0. At t goes to infinity, VL equals 0. So e to the minus whatever is doing the same thing for the capacitor and inductor. So what happens at tau equals L over R? Well, L over R and R over L cancels to 1, so you've got e to the minus 1 again. So that equals about 36%. So the inductor has charged to about 63%, and 36 is about left over from 63. So the back EMF started at 100% and it has gone down by 63%. The back EMF has been reduced by 63%, that same time constant. And so they say, once again, that 5 times L over R is about 99%, I can write, of the way charged. And once again, you're gonna see this in other forms, and you won't see, if you look this up, you won't see this as a voltage, you'll see this as a current. I just divide it over so it's voltage. The point is to talk about the back EMF. This is the formula for the back EMF. So, we trust the smart people to have applied Lenz's law and all this other stuff to get this formula correct. I'm simply showing you this e to the minus t and whatever, which is your tau, shows up in both the capacitor and the inductor, which is why you have the same kind of time constant, the same kind of curve, and you can use both of them in the same kind of way. So what happens if you put capacitors in series? If you just have a capacitor and so forth in series. Let's say series and parallel here. That's an R, or is trying to be. 1 over the new capacitance, or the combined capacitance, is the sum, let's just do it simpler. I won't use the fancy math notation, we'll just say 1 over C1 plus 1 over C2, and so forth. Now you may remember this kind of math from the resistors. Resistors in series is just you add them, and then resistors in parallel you reciprocate them all and add them and then reciprocate again. Same math, different thing. In parallel, when you have a rail and a capacitor across it, and then another one like this, in parallel, the parallel capacitance, and I'm not going to derive it, this is not a physics course. Once again, we're trusting the smart people. You just have the new capacitance is C1 plus C2. For an inductor, guess what? It's the opposite. The new inductance for series is L1 plus L2. For parallel is 1 over L1 plus 1 over L2. Inductors in series and capacitors in parallel just add their capacity. Inductors in parallel and capacitors in series also add by this fancier formula. How do we conceptualize this? For a capacitor, think about surface area. If you have two capacitors in parallel, you could kind of think of just sticking their surface areas together and you get double the surface area, assuming they're, don't get into the physics, just the analogy. I'm just explaining. But conceptually, you can think in parallel, you're just kind of adding their surface areas together. So that would just increase the capacity very simply. Whereas if they're in series, you've got, electrons being pushed. Let's say your voltage is like this, so negative voltage over here. So electrons are being pushed this way and they're being pulled this way, but in between them, they're being pushed from one to the other, and there's a complex interaction there, so it doesn't quite just add up. What about an inductor? Let's say you have an inductor and another inductor. So you put a certain voltage across this inductor and you're trying to charge it up, and there's going to be an EMF from the battery and a back EMF from the charging process. Well, instead of that, let's say you have the voltage across both of them. So you've got your EMF way across here, and they're each going to try and put a